This meeting is being recorded.
In Chapter 16, Section 5, we're going to take a look at thermodynamic versus kinetic control, specifically with respect to the 1,2 addition products and the 1,4 addition product. So a thermodynamic control, that will generate the more stable product, and we'll see that a kinetic control will generate a faster product. So that's a way that we can differentiate between these two types of controls. So the ratio of our 1,2 versus 1,4 addition product to this HX addition reaction shown below is, we're told it's highly dependent on temperature. So at lower temperature, what we see is actually the faster product form, right? We'll see this 1,2 adduct in a higher percentage than our 1,4 adduct. And at a higher temperature, we're going to see that we have our thermodynamic or more stable product form. And this ratio, again, at higher temperature shows the 1,2 adduct at a much lower percentage than at the lower temperature. So let's take a look at an energy diagram to try to gain some reasoning as to why this happened. So I mentioned that the 1,2 adduct occurs faster, and we say that this is kinetically favored. Kinetics having to do with reaction rates. So what we see here in our potential energy diagram is our starting material here, the 1,3-butadiene. We see this proton transfer step and pretty equivalent activation energy needed, right, to gain this carbocation intermediate here. So once we reach this step, this is where our two processes differ. At the nucleophilic attack stage, the 1,2 adduct, you can see, would happen, again, more commonly at the lower temperature, and this would be a faster reaction requiring less activation energy here. So we would generate this 1,2 adduct at lower temperatures in higher percentages. Versus our 1,4 adduct, which if we have more energy required for this activation here, for this pathway, right? Notice we have that higher activation energy for the red line. We can actually produce the more stable, the thermodynamically favored product, as we see down here with our 1,4 adduct. And the reason that it is more stable, the 1,4 adduct, is because it is more highly substituted. It's a more substituted alkene, right? We see if we were to fill in hydrogen, sometimes it's a little clearer, right? So we have a, again, our more highly substituted alkene shown on the right here. So this will be why we have the 1,4 adduct becomes more stable because it's the more highly substituted alkene, and this would be then the major product at higher temperatures. And we could say that at higher temperatures, we are using thermodynamic control to generate this as our major product. So again, how can we control these reactions? The 1,2 adduct forms faster, and we assume that that is due to really just simplicity of proximity. So when we have this protonation here shown in this first step, at our carbon 1, we generate this resonance-stable carbocation intermediate here, and this bromide ion, rather, after protonation is in this location to a carbocation versus in this location to the carbocation on carbon 4 here. So you can see in this exaggerated sketch here that this bromide over here is closer to carbon 2 than it is to carbon 4. So that's why we generate this product faster. Again, it's said to be under kinetic control at lower temperatures. And this product would then be our major product at lower temperatures. And we can say it's under kinetic control. So there's another reaction shown here on this slide, which is a special case, or actually two reactions, we should say, that are special cases of a 1,4 addition. So say we have this monomer here, and we could number our carbons 1 through 4. This isoprene monomer, through a polymerization process, can produce this natural rubber compound, the cis-1,4 polyisoprene. So again, we have isoprene generating polyisoprene, a species down below. Then we have chloroprene, and similarly, if we were to number our carbons 1 through 4, we can see this special 1,4 addition through this polymerization process to go from chloroprene. So on carbon 2, we have that chlorine, to what we call down here in the polymer form, neoprene, or trans 1,4 polychloroprene. This is a form of synthetic rubber. So we will look at another distinct type of reactions in section 16.6 in the next video.